Welcome back to NET Physics series. Today we'll be continuing with chapter of electrostatics, and the goal is to solve some of the past paper questions from electrostatics. So here we have question number 1, and it reads that the electric field intensity at a point 20 centimeters away from a charge of 2 times minus 3 coulombs is what? So picture a situation something like that. You have a charge, and let's say at this point the charge is q, and there is a point that is some distance that is 20 centimeters away. So let's just call this point P. The distance from this charge to this point P is of 20 centimeters. Now note that all of the options that you're given are in newtons per coulomb, which means that they have been using SI units, which means that the SI units for distance is meters. So you'll have to write this in meters, which would be 20 and into 0.01 meters, right? Because that's a centi, which would become 0.2 meters. So that's the distance. Now we know about electric field, that the electric field is directly proportional to the charge that is going to produce this electric field. Let's call it capital Q. And we know that it follows, or it obeys, the inverse square law. So it's direct or inversely proportional to R squared, which means that the electric field expression would look something like a constant multiplied by Q and divided by R squared. This constant, we know it's called the Coulomb's constant, and the value is given to you. So the charge is 2 into 10 raised to power minus 3 coulombs. So that's what I'll plug in for here, 2 into 10 raised to power minus 3 coulombs. And for R is the distance between the point P and the charge Q. So in general, whenever you're computing the electric field at any point, R is the separation of the point from the source charge, which is producing or giving rise to this electric field. So then in place of R, we'll substitute how far is the point away from this charge, which is 20 centimeters, which is 0.2 meters. So I'll square this and put this value over there. And then writing the constant value for K constant, if you do the math, this thing evaluates to 4.5 into 10 raised to power raised to power 4. So you can see that that's the option A, 4.5 into 10 raised to power 4 newtons per coulombs. So of course, don't forget the units when doing the calculations. All right, so that's question 1. Now let's move on to question number 2. It says that on removing the dielectric from a charged capacitor, its energy either increases, decreases, remains unchanged, or none of the above. So once you remove the dielectric from a capacitor, does it have any effect on the energy? First, think about that. So, well, we know that once you remove the dielectric from a charged capacitor, it has an effect on the energy that the capacitor can store. The energy stored would be increased, and the reason for that is that once you remove because the capacitance will start decreasing, and we know that the expression for capacitor and charge is Q is equal to C times V, where Q is the charge, C is the capacitance, and V is the potential difference between the plates of the capacitor. So of course the charge is going to be a constant. So if capacitance decreases, then the voltage or the potential difference is going to increase. And if potential difference increases, then the energy is going to increase, because we know that energy is directly proportional to the potential difference between the two plates. And hence we conclude that once removing the dielectric, it causes a decrease in capacitance, which in turn causes an increase in the potential difference, which finally gives you an increase in energy. Hence its energy will increase, and that's part A. Alright, so now let's move on to question number 3. And we have A and B are 2 points in an electric field. So let's try to picture this. We have 2 points A and B, and there is some region of electric field where these 2 points are placed. So if the work done in carrying 4 coulombs of electric charge from A to B is 16 joules. So you have a charge at this point, at this A. So let's draw it as a circle, and it's 4 coulombs. You're taking this charge from point A to point B. And once you take it to point B, they're telling you that the work done is 16.0 joules. They're asking you the potential difference between A and B. So we know what charge we are taking. We know that that's 4 coulombs of charge. We know that the work done to take this charge from a point to another is 16.0 joules. So let's write this down. They're asking you the potential difference. Now you have these 3 quantities. You'll quickly see what is an expression that relates all of these quantities. So we know that that's the expression for work done, because we know that work done is given as the charge that you want to take from one point to another times the change in potential difference, right? So, or we can just call it potential difference. There's no such thing really as change in potential difference. So this potential difference is what we want to compute. So let's just factor this thing out, and we get the work done to take the charge from A to B divided by what charge that you are taking. So that's Q. So this would be 16.0 joules divided by 4 coulombs of charge. We know that that's 4.0 joules per coulomb. So that's 4 joules per coulomb, but we know joules per coulomb is defined as volts, right? So that's just 4 volts. And so we see that that's option C, 4 volts. So that's the correct answer to this problem. Now, moving on to question number 4. So we have that a capacitor of capacitance C is connected to a battery of EMF V0, right? So we are given the capacitance C, we are given the potential difference, it's V0, or the EMF, which is the electromotive force of the battery. Without removing the battery, a dielectric of strength epsilon R, right? So the strength of the dielectric is given as epsilon R, is inserted between the parallel plates of the capacitor. So we can assume a situation, picture that as these are the plates of the capacitor. Suppose these are positively charged and here we have negatively charged. Now what we are doing is we are inserting a dielectric material between these plates, and the strength of this dielectric material is given as epsilon R. Alright, so then the charge on the capacitor is, so they're asking you about the charge on the capacitor. So what do we know about charge and the EMF? What relates these two things? So we know that that's the equation Q is equal to CV, right? Now we know that if I'm inserting a dielectric material of strength between the capacitor, it's going to cause a change in capacitance, right? And the change in the capacitance is measured as the strength of the dielectric material times the original capacitance. So this is the change in capacitance. Let's call it C prime. So this, by this amount, of the strength of the dielectric, the capacitance is going to either increase or decrease. But we know that the strength of the dielectric material is normally always of the form which causes a decrease in the capacitance, right? All right, so now the EMF of the battery is V naught, right? So the potential, we can write it as V is equal to some value V naught. So now let's just substitute all of these back into this equation, and that gives you the charge as epsilon R times C for the capacitance. So this is all for C, this thing C, right? And then we have voltage, so that's V naught. So that's the charge on the capacitor. So we can see that the charge on the capacitor is from all of these options, it should be the product of all these quantities, and that's option B, right? So we have epsilon R times C times V naught. So the correct option is option B. All right, so moving on to question number 5, we have which of the following graphs represents the relationship between the force and the force between 2-point charges and square of distance between them. All right, so what do we know about the electrostatic force? We know that the electrostatic force is directly proportional to the charges which experience this electrostatic force. So let's call Q and another charge, let's call it small q. And we know that it follows an inverse square law, which means that it's inversely proportional to the square of the distance between these 2-point charges. So that's what we know about force, the relationship between force and charges, and the relationship between force and the distance. Now, if you look at all of these options, all of the graphs are given a relationship of force versus distance squared, right? So it's force versus distance squared. This thing is very important. You're supposed to note that this relationship, the graphs are plotted with force on y-axis, and on horizontal axis, it's not distance, right? It's the square of the distance. Which means that you should be looking for a graph that is a straight line moving downwards, right? It will not be a curve, because on the horizontal axis we are looking for distance squared and not distance, right? So it would be 1 over r squared, and because it's 1 over r squared, right, so it is an inverse relation, which means that the right graph for this would be a line that goes that's when it's closer to 0, distance is closer to 0, at that point the force is maximum, and when the distance increases, then the force starts decreasing. All right, so these numbers are pretty unclear, right? Actually, this is distance to the power 1. This is distance to the power 1. This is also distance to the power 1. This one is distance to the power 2. Now you might think that the correct option is option C, but that's not the case, and the reason for that is the graph is touching your force axis when r is 0. But you know from the expression that clearly when r becomes 0, at that point force is undefined, or it reaches, or it goes, it keeps on increasing and increasing, and it would never touch the force line, right? The force line really starts acting or behaving as an asymptote at that point, right? So which means that this is not going to be the right answer. Now if we look at all the other options where distance is plotted with the power 1, at that point we can see that of course it will not be this one as well, right? Because it's a straight line, but we know that we're given a relation, inverse relation between r and f, right? So it cannot be this graph as well. This one is a linear graph. This one, even though it is a graph which is not linear, but you can clearly see that this graph shows that as the force as the distance increases, the force will increase. But clearly that's not the case due to this relation that we have established. Hence, if you look at this one, you see that as distance increases, the force starts decreasing with square, right? And it never touches the force axis. It keeps on increasing and becomes parallel to the force axis. And the similar thing is happening when the distance is increasing. The graph becomes parallel to the x or the distance axis, which follows this relation, and hence the correct option is option D. Alright, so now let's move on to the next question, which is question number 6, and it reads that capacitance with air is 10 farads. So we're given the capacitance when air is present. If a dielectric of epsilon r is equal to 100 is inserted, then the new capacitance would be what? So, well, clearly the situation is that you have two plates of capacitor and these are parallel to each other. So suppose you have positive charge over here and negative charge over here. You're at this point, before the dielectric is inserted, the capacitance is given as 10 farads. The next situation is that you have the same arrangement with capacitance of 10 farads, but now what I do is I insert a dielectric medium between these two plates, and the strength of this dielectric medium is 100. Now note that this is a dimensionless parameter. Alright, so they're asking you the new capacitance, right? So really you can say that the modified capacitance is being asked, and we know that the modified capacitance, as we discussed just a few minutes ago, can be written as the product of the strength of the dielectric times the original capacitance. So all we have to do really right now is multiply this 100, which is the strength of the dielectric, with 10 farads, which is 1000 farads, right? So we can see that the correct option is option A. So this was pretty simple. Alright, so now let's move on to question 7. They're asking you that the amount of work done in joules in carrying a charge Q along a closed path PQR. So this path is closed. This is a keyword over here, right? So you can see that the path is closed as in this figure. This starts from P, goes to Q, then goes to R, and then goes to S, and then goes back to P. So the path is P, Q, R, S, P. Alright, so between the oppositely charged metal plates, so clearly we can see that this is positively charged and this is negatively charged, and the electric fields between the plates is just some E. So they're asking you the work done taking a between you can say if you have a charge and you take it from this point and take it to Q, R, S and P. Now this path is closed, right? And we know that the work done in electrostatics, if the field is conservative, right? The electric field, it's a conservative field. So if the path is closed and I'm starting from this point P and coming back to this point P, then the closed integral of f dot ds is going to vanish. And this closed integral of f dot ds is defined as the work done by a conservative field, which is going to vanish. Hence, the work done in joules or whatever would be then 0, right? Because it's vanishing. Hence, the correct option is option A. Alright, so moving on to question number 8 over here, we have that a thin metallic sphere shell carries a charge Q on it. So there is a spherical shell, it's made up of metal, and on the surface it has a positive Q charge on it. A point charge Q is placed at the center of the shell. So you're putting a charge Q at the center of the shell, and another charge you're putting it outside the shell some distance away from the surface of the shell. All right, so we are also given that all of these charges are positive. So all of these charges that you see over here, they're positive. Now they're asking you the force on the charge at the center. What force will the charge that is placed exactly at the center of the sphere would be? So what do we know about spheres? We know that at the center of any metallic sphere, the electric field vanishes, right? So the electric field would be 0 at the center. And if electric field is 0, then the force, which is just Q times the electric field, would also vanish. So the correct option really is that if there is no force acting at this charge that is placed at the center of the sphere, because at the center all the electric fields would really cancel out each other, and the vectors, the sum of the vectors would be 0, and hence the electric field is 0, which means that the force is 0 as well. Alright, so moving on to question number 9. If F is the force between 2 point charges that are submerged in a medium of dielectric constant K. So suppose that you have 2 point charges. Suppose this is point charge A and this is point charge B. Both of these charges are submerged in a dielectric medium, something like this, whose constant is capital K. Now when you withdraw the medium, then the force between the charges would be how much? So at this point, when they are in the dielectric medium, the force between these two charges is F, right? So suppose that I withdraw the dielectric medium, what instantaneous force would these 2 point charges experience? So we know that the force, how it is affected, the force is decreased by adding the dielectric medium in 2 charges. The force between the points will decrease by this factor of K, right? So the new force is the original force divided by K. Now this dielectric constant K can also be written as epsilon R, right? So it's the same thing that we have been discussing in previous problems as well. And so if I want the force as when I remove the dielectric, that is this force F. So I'll just rearrange this expression for this, which becomes K times F prime. Hence the force as soon as I remove the dielectric medium would be the dielectric constant K times the force that was there when the dielectric medium was placed in these 2 charges. So that's F times K. So that's correct option B. Alright, so now let's move on to question number 10. 2 plates are 1 centimeter apart and the potential difference between them is 10 volts. Alright, so we have 2 plates. Let's draw this thing. And so these are the 2 plates. The distance between these 2 plates is given as 1 centimeters, right, which would be 0.01 meters. And the potential difference between these 2 plates, delta V, is given as 10 volts. The electric field between the plates is what? Alright, so you just need to know at this point the expression for the electric field and potential difference. So what relates electric field with potential difference? We know that that expression is simply that the potential difference is given as electric field between the 2 plates times the distance between these 2 plates. So you are required to find the electric field, right? So just rearrange this expression for electric field, which would be the potential difference divided by the distance between the two plates for which you want to compute the electric field. And so just doing the math now really by putting in values would be delta V is 10 volts, right? Now D would be used in terms of meters, right? Because you can see that all of these quantities, all these options, they are given in newtons per coulomb, which is the SI unit. So the SI unit for distance is meters, hence you would be using 0.01 meters. And if you do the math, this is simply 1000 volts per meter, which is also 1000 newtons per coulomb. So the correct option is option C. Alright, so now let's move on to the final question, which is question number 11, and it reads that an electric field exists in a space between two charged metal plates. So you can see that there are these two charged metal plates. One is positively charged and this one is negatively charged. Alright, so which graph shows the variation of the electric field strength E with distance d from x along the line xy? Alright, so what do we know about electric field or electric field strength? These lines that you have between the plates, these lines are telling you about the electric field strength, right? So the more these lines are, or the closer these lines are, the more the electric field strength is. Now all of these lines between these two plates, which are placed a distance apart from each other, these lines are always uniformly arranged, and so we can say that the electric field between these two plates would be constant, understanding from the behavior of these lines, right? So all of these lines would be arranged at a particular, you could say, distance. So this distance between all of these lines is always going to be a constant distance or a constant value, which means that because these lines are giving you some information about the electric field, then the electric field should be constant in respect to the distance between these two plates. Let's call that d. So if I have a graph between the electric field and distance, then at every distance the electric field should be a same value. So suppose it's a particular value at this point at some distance, and at this distance it would be the same value, at this distance it would be a same value. And so similarly for this point also it would be this one, and once I join these points like this, so it would become a straight line, and hence the electric field, which is constant, is represented by this graph, which is this one, C.